Okay, so in this video, I want to do a quick demonstration of the idea behind the definition of the derivative. So let's say that we have a function, oops, zooming in too close. We have a function like this black curve here, which is y equals x cubed minus x. And let's say we want to find the derivative or the slope of the tangent line at the point 0, 0. Okay, so that a equals 0 is saying I want to find the derivative or the slope of the tangent line at 0, 0. So I think we've alluded to this before, that what you would want to do is calculate the slope of the secant lines between this point 0, 0 and then this other point, which we were calling f of a plus h, h comma f of a, sorry, a plus h comma f of a plus h, right? So we're trying to find the slope of these secant lines, and then the intuition is that if h is big, if the distance between the point where you actually want to calculate the slope and that other point is really big, then it's going to do a bad job of approximating the slope of that tangent line. But if you let it get smaller, all right, if you take the limit as h goes to 0 of that difference quotient or that rise over run calculation, then it's going to get better. And so you can see now this is starting to look like a better approximation, and I can kind of slide it in and you see it's getting better, it's getting better. And as h goes to 0, it becomes a really good approximation for the slope. And if h actually goes to 0, then it becomes the perfect approximation for the slope. So that's kind of the idea behind the limit definition of the derivative. As long as the increment h is small, you get a really good approximation for the slope of the tangent line. Okay. Another